valve to adjust the volumetric flow rate.
For a given power.
Yes, you restrict it. Right. So that's how you change the Q, which is the next topic we will talk about. Right? Any other question on how the Moody diagram comes about? So I very briefly hinted and mentioned that. So how come in the laminar flow you can come up with this nice closed form expression that relate the delta P to the important perimeters by solving the Navier-Stokes equation, or the equation of viscous motion, but in turbulent flow you cannot. The answer to that is why continuing after a century of fluid mechanics study, people still have to hire you to solve fluid problem in a gas turbine or in a nuclear power plant or in anything that relates to fluid flow. It's not an easy question to answer, but do you understand the question? So for laminar flow, where they behave in layers, they are so well organized, the equation of motion can be directly applied to that fluid flow. But for turbulent flow, all the velocity consists of two components. This is more like advanced fluid, graduate level fluid. All the velocity that we talk about in the context here have to be broken down into a mean component, steady component, and a fluctuating component that's highly time dependent. Because although turbulent is just dancing around maybe in kilohertz type frequency range, and the equation of motion is not capable of including this time dependent term. And everything becomes purely experimentation. The equation cannot be solved exactly. So this is what is called a turbulent model. And billions of dollars used to understand how that works, and still a black art. And that's the job for you. That means, hey, I just cannot do this on a computer. I have to go to a lab and do experiment for any new application. Okay? So that's the sidetrack, there's a tangent, but I thought, put it in perspective, you may appreciate that. Okay, so next topic, minor losses. You ready? So we just now have to deal with other component in my flow system that must account for So I will set an example problem by giving you the statement of the problem, and then we will give you some additional background as to how one can tackle a more complex flow system. So I'm trying to pump water from a lower elevation to a high elevation by way of the water tank. In total, the water level between the two tanks has an elevation of 20 feet, and we're doing with water. The flow rate given, just like that schematic or roadmap. We're going from left to right, so the geometry, the flow rate is given. So this flow system is a little complex. It has two 9-degree elbow, and the plumbing consists of galvanized iron, 2-inch diameter. Total length is 60 feet. And galvanized iron if you look up in the table, have a roughness of approximately 0.005 feet. And the way the water is being pulled into the pump and the flow system is via a rather peculiar name. It's called a re-entrance entrance, meaning that there's no attempt to smooth the flow that gets pulled into the pump. It's a sharp intake, and the water is not very efficiently being sucked into the flow system. You can imagine if I have a very smooth bell mouth, instead of a sharp intake, I have something like this. It may be easier for the water to get sucked into the pump, but we have a very different device. It's just a sharp pipe deep into the water. The exit also have no attempt to smooth the exiting flow. It's just a pipe dumping into a tank at an open angle. We call it a sharp exit. With all that is given, and this time you were told the pump is not 100% efficient. Instead, it's only 70% efficient, meaning only 70% of the electrical energy I put into the motor get transferred to the water. The rest just get dissipated and become lost. Tell me, with all this given, how big a pump in horsepower is needed to make this flow system work. That is also, in layman term, being referred to the brake horsepower. What that means is the actual power consumption. The electric bill you have to pay to run the pump with 70% efficiency to make the flow go from the bottom tank to the top tank. So how is that different from the gasoline pumping pump? In two aspects, yes?
Well, you have like angles and that sort of thing. It's not just a straight pipe.
Right, I have now more devices. I didn't mention that. So I have also a valve. This is a symbol for a valve. It happens to be a gate valve, which is nothing but a circular plate in the middle of the flow of the pipe. By raising and lowering the gate, I can control the flow rate, the velocity of the tube. So all those added components, the elbow, the intake, the exit, and the valve, do they create more pressure losses or less? Do you have a feel for it? More, because they are resistant to my flow. The water has to overcome all those devices. And because of that, it leads to what we call minor losses. All practical pumping systems will have minor losses. It's still constant density. And what I meant by minor losses is the fact that there are now additional pressure drop. Delta P is dropping, so then I can overcome other components due to such as what? Entrance or exit. So for aircraft engine, the nacelle, the inlet section is always very smooth, contoured to allow the flow to be pulled into the compressor with very little pressure drop. But for other applications like pumping water, you don't care spending a little bit more energy, power. You just have a sharp exit or sharp intake. So entry flow and exit flow have pressure drop or losses associated with that. A valve that is used to control the Q, the flow rate, can be fully open, partially open. If it's fully closed, then you have zero velocity, no Q. And symbolically, that's just a circle with a cross. It's a pipe. And then, last but not least, are all the bands and elbows that, because of friction, when the fluid goes through those devices, that 90-degree band, due to friction, they can generate considerable losses. Okay? So how do we account for those is the subject matter now. And once I can do that, then I can go back to that problem and kind of look up for each of those components, the valve, the elbows, the inlet, the exit, what is the estimated losses due to each of those? Yes?
So minor losses as a whole are just, they're still technically frictional losses, just specific to a certain component?
That's very well said. So let me make sure I don't miss that. So what is really so-called minor losses? Those are the losses that I cannot represent in the Moody diagram. Why? Because the Moody diagram is purely due to frictional shear on the plumbing, on the surface of the plumbing, and the valve, the intake are actually a slightly different mechanism due to flow separation. Alright, because the length and the shear created by that section of plumbing is relatively small. It's not a whole 9 miles of piping, but it's just a sudden turn of the flow. And when there's friction involved, the fluid cannot have any means of following that 90-degree turn. So if I look at some of the detail, the flow come in around this corner, the flow will separate it. And that separation is what creates losses, not purely due to shear, not purely due to friction, due to the fact the fluid doesn't want to follow the contour. Okay? So that is the kind of losses that we are now tackling, not purely due to shear and friction, but other flow mechanisms. Yes?
How do you distinguish between minor and major losses?
The word minor is actually very deceiving. So first to answer your question, when I say minor, is anything but Moody diagram losses. Right? So Moody diagram is specifically just like the homework you have done where you're trying to estimate the friction factor for that water pipe problem. We'll go for that again. But that is purely due to skin friction on the inside wall of the pipe, of a straight pipe, resisting the flow due to the boundary layer. That's all we are doing with Moody diagram. Anything beyond that, like those devices, is not purely due to shear losses. We call it other losses. But instead of doing other, we say minor. You will find by way of this example that the actual so-called minor losses for this example is actually greater than the Moody diagram losses by far. Oh, so the word minor is deceiving. Yes?
So in the example you drew on the board with the 90-degree elbow, it comes around the bend real sharp and it makes that little swirl.
Yep.
How big could you make like a turn, like so instead of a straight elbow,
Yep.
could you make like a semicircle?
Yep.
Like how big of a semicircle
Yep.
to the point where it becomes negligible?
So next lecture I'll answer that.
Okay.
No, that's a good question. There's different elbow. This is maybe the worst elbow. There are others that you have a huge radius, relatively smooth, and you have less losses than this one. It's just like the intake. The diagram there shows a sharp intake. I can have a bell mouth intake like this one, very smooth, so the flow can follow with minimum separation on the edges. Like for that intake, because of friction, the flow will separate and create some losses right at those corners. Because the flow, the real flow with friction cannot negotiate a sharp corner. And that kind of separation is what we are trying to account for, and you pay for it. That's pressure loss. So for aircraft engine, where every ounce of weight is accounted for, not even pound, you want to minimize those losses. Yes?
So how will we know when to account for minor losses?
You always have to, for any realistic flow system, how to account for it is what I will show you next. Right? The table you can look up depending on the geometry of the device, and it's all empirical. But they are work done before, so you can look up for a given device with a valve that is a gate valve that is 50% open with this diameter and so forth, what is the estimated losses due to.
So like the previous one that we did on the homework, the ideal system?
Say again?
The previous one we did on the homework where we didn't account for minor losses?
Yeah, all those are just not idealized, but for a horizontal pipe with nothing in between the inlet and exit, no valve, no elbow. All I'm doing was sheer frictional losses that are accounted for by the Moody diagram. But no flow system ever do that. You always have the valve to control the flow. So we start simple, but now we're adding compressivity to make it more realistic. Yes?
So are these the only things that are accounted for in minor losses? Because there was a question on the homework that asked about possible pipe with debris in it. And so would debris be accounted for by Moody diagram, or would it be?
There will be a very special case that will not be accounted for either of these. That become somewhat a different losses that you have to find a means to account for them. And I don't think we will be going in any length into that at all. Okay? So that is a background now, what people have done. This is all purely empirical and experimental. Experimental means if I'm a valve manufacturer and I'm trying to sell you an equipment, a valve that you can control your flow in your Alaska pipeline or in a chemical refining power plant, I have to tell you how much losses is to be expected if you buy a ball valve or a gate valve from me, 7 centimeter diameter, so that you as an engineer can use those data to estimate the pumping power. And the way this is handled is to define a new term called minor head loss. That is different from the frictional loss that we have talked about. And the definition is, again, the equivalent head or length. And that delta P is the pressure drop through the device, which I can measure in my manufacturing plant for different type of valve, for different sizes. And upon that, I can generate a dimensionless, low unit perimeter called a loss coefficient, K. It's no unit. Can you see that it's no unit? Length divided by V squared divided by gravity. Okay? So my job then as the manufacturer of all these devices that I'm trying to sell to you is to give you those K value. And as an example, just one example, a 45-degree elbow and depending on the turn radius relative to the pipe diameter, the K value may be something like 0.4. And those are all tabulated, and in chapter 8, you'll find all of those. In the next lecture, I'll give you some example of different losses for valve, pipe, turn, intake, exit, and for 90-degree turn, which is more severe, and you expect more losses. And again, depending on specific geometry, the K value could be 5 times more, et cetera, et cetera. So all those are given to you in the form of the table lookup. And the manufacturer of which you're trying to buy the equipment from will have to provide that, so you can estimate it. Yes?
Just a quick question, what's the subscript from the B in that K equation?
Sorry, from that far on, that's the velocity, first of all, so the numerator is the minor head loss, x sub m, denominator is average velocity, v average, squared, divided by 2 times gravity. The 2 is just by convention. But the denominator, if you look at the unit, is length. Yes?
On a test, would you give us the K values? Or
Either that or I'll give you a chart that you can use to look up, but you'll be given, just like the Moody diagram, I don't expect you to memorize the Moody diagram, but you will be provided, yes. So, once you have the K value, which is all that is given for that problem, and I'll give you those momentarily, the last step to close the loop, to account for those losses, will be to go back and calculate the equivalent head loss due to those components. So K is a given. If you tell me the geometry and the value you have, I can look it up. You already told me the velocity or the flow rates, then on which I can use this equation to now estimate my so-called minor head losses. And you can compare that with Moody diagram, frictional head loss. As a contrast, the perimeter is the difference. The Moody diagram frictional head loss resulted in the use of friction factor and the length diameter. Now, due to separation of flow, not necessarily just shear stress, all that now is replaced by a dimensionless coefficient called loss coefficient. And that has to be provided and problem dependent. Okay? So as an example then, with all the components